Thank you very much for connecting to this webinar. We will be discussing and seeing 4 very interesting projects revolving around non-battery based energy storage, which are basically for sustainable solutions. Just a quick brief of the agenda. In the first place, we will have Soren Bowat, who will be doing an overview regarding the non-battery based energy storage sector. Then we will have the opportunity to listen the project coordinator of RECYCALYSE, who is Christian Kalusev. And then we will have the chance to listen José Luis Viviente, who is the project coordinator of AreNHa. Then we will have a 10 minutes break. And later than the break, we will have the opportunity to listen Jens Oluf Jensen, who is the project coordinator of Next AEC, and Daniel Garcia, who is the project coordinator of Promet H2. And last but not least, we will have a breakout session where you will be able to ask, and we will also will be doing a wrap up and sharing the conclusions of the workshop. But before I start, I would like to inform you that this webinar is being recorded. I would like to reinforce with you to make sure you please make sure your microphone is mute. And if you encounter any issue or any problem, please use the chat function to let us know. Okay, so we can fix it. As well as if you have any question regarding the topic, you can let us know through the chat, and we will share at the end of each presentation. So feel free to participate because we want to make this webinar very interactive. Who will talk today? First of all, we will have Soren Bowat, as I said. He will be giving us the introduction of the sector. David Bauer is the acting head of unit from the industry unit of the Health and Digital Executive Agency in Brussels, which is responsible for the implementation of the industrial research and innovation legacy activity from Horizon 2020, as well as the industry activities in Cluster 4 of Horizon Europe. He has more than 20 years working in the European Commission. So he will, we think that this is, he is the best person to this, the overall view of the energy battery sector. Then we will have the opportunity to listen Christian Kaluf. He's the director of the Center of Nanoproduction and Microanalysis at the Danish Technological Institute, and he is as well the project coordinator of RECYCALYSE. José Luis Viviente is the project manager and senior researcher at Tenalia, and he's now coordinating AreNHa project. Jens Oluf Jensen is professor at Technical University of Denmark. He's coordinating the Next AEC project. And Daniel Garcia is senior staff scientific at the Institute of Engineering Thermodynamics of the German Aerospace Center, coordinating the project Promet A2. So now is the opportunity to listen Soren Bowat. So Soren, the floor is yours. Let me stop sharing the screen, and so you can.
See. Oh, wait. Okay. So can you see the slide?
Yes, we can.
Okay, very good. Then let's start. Okay, thank you for the introduction, Pablo. I'm honored. I'm very happy to be in this meeting. I think it's a very good initiative that you have made. to gather all the expertise around non-battery energy storage. Actually, the topic came about already in 2018, perhaps even before that, when we were dealing with lots of different other things to achieve the emission reduction and the new forms of energy, renewable energy things, because we realized that everyone was talking about batteries, and batteries may be very good for charging your mobile phone and perhaps even going around in your car and other things. But in reality, it was very easy for us to see that batteries would simply not cut it in terms of real energy storage, simply because of two things. One was the capacity of energy storage in the batteries. It was not even at the scale where we wanted it to be able to adapt or to store the surplus energy that we needed if we would go all the way to sun and wind energy, and in general all the different renewable energy sources. So that was one reason, and the second reason was the time, because we are dealing with different time periods for the storage, and batteries is just one time period that you can use. And it's not a long-term storage like that, simply not in the capacity. So that's why we saw the need to develop alternative technologies to be able to deal with this problem. And the obvious choice already at that time was, of course, either power to gas, power to chemicals, or power to liquids, also popular called power to X, simply because of the amounts that we needed to store. There were other things, like in other time periods, like compressed air energy storage, which could be used in the same manner, but it's a different time segment. And therefore, we needed to be able to cover the full time span of energy needs. And one of the fundamental things about doing this is, of course, that we needed improved materials that had increased performance and also a reduced cost in respect to the available ones. And this is not something that comes easy. I mean, we can come up with new materials, but generally at the beginning, they're always more or much more expensive than the ones that are there. And therefore, we simply needed to bootstrap this thing to be able to make new materials, and in combination with new designs, architectures, and for instance, also reduced maintenance needs in order to be able to overcome this. So therefore, this was a very, very important topic for us at the time. And I think that it actually remains a very important topic. So what we've started with this call is by no means the end. And that's why we need to pursue these goals also in the new framework program, Horizon Europe. And here we're going to be very ambitious in what we do in comparison to Horizon Europe, because we're going to change the strategy a little bit. So we will focus on scientific and technological excellence and strengthen the whole fundament for this in science and technology. And therefore, we also need to tackle political or policy priorities. This we've not really done to the same extent before. There we were doing point sources. We were doing a little bit here and a little bit there, but we were not really connecting the dots. Today, we need to connect the dots in the whole value chain in order to be able to do this. And that means taking into account also the society as it is and the economy, investments to boost the innovation uptake and competitiveness. And therefore, we also need to make sure that everyone has a job, because otherwise it doesn't really matter. So the vision that we are pursuing is simply to have a sustainable, fair, and prosperous future for the whole of this planet. based on the values that we have. And it's not that we are going to go out and tell everyone that what they should do. I think that we need to spearhead this and show how it can be done here in Europe. And that, of course, involves first and foremost to be able to tackle climate change. And for this, we actually want to use, or we have a political commitment to use up to 35% of the total budget of Horizon Europe. And it's going to be needed because I think that the challenges ahead of us are much, much bigger than anyone realizes. And at the same time, we need to achieve more of the sustainable development goals so that people, they feel that we're actually doing things not just in one area, but we are making sure that they also have a livelihood, they have a house to live in, they have a good, decent life. And the means, as we see it, to achieve this is to boost the union's competitiveness and its growth. Just some few things about the budget. And in this presentation, I'm not going to give you a whole overview of the energy sector or things like that. What I'm going to do is give you a feeling for the philosophy that we have developed in connection with this Horizon Europe, which has, as you can see, a pretty impressive budget. At the moment, we have a budget of 95.5 billion euros, which is significantly bigger than Horizon 2020. But there is one little thing in this that we've not really sort of depicted at this, and it's that this is before the third country contributions. So it's likely that Horizon Europe is going to be significantly above 100 billion euros. That means we have serious amounts of money available for us that covers the whole envelope. And that means not only the research in itself, but also the investments that are needed and the insurance that we need to be sure that we can actually fund these projects, even in a hostile environment. And it covers 3 pillars: excellent science, global challenges, and European industrial competitiveness and innovation Europe. So I think that many of you have already seen this, so I'm not going to dwell on this very long, just so that we are all aware where the different things is. As I said, there are 3 pillars. You have the excellent science, under which you have the European Research Council, you have the Marie Curie fellowships, and you have the research infrastructures. And then you have a big pillar, which is pillar 2, which covers all the global challenges and the industrial competitiveness. And then finally, you have pillar 3, which is innovative Europe, which consists of the European Innovation Council, the European Innovation Ecosystems, and the European Institute of Innovation and Technologies. And together, all these things, they actually cover most of the things in Europe in terms of research and innovation, and also investments for industrial technologies. But of course, we cannot do this without other kinds of actions, like, for instance, we have in the Euratom, where we have fusion, fission, and we also have the Joint Research Center that is helping us with this. And we cannot do this also by ourselves. We need to reach out to other parts of the world to make sure that we are all following the same line. So one of the most important parts of Pillar 2 is the Cluster 4, because it includes some of the activities which are important for the industry. And that means we are 4 DGs that are working this together. It's DG Connect, it's DG Grow, it's DG RTD, and it's also DG DEFIS. And what we're going to try and do is to accelerate the twin transition, as we normally call it, which is the green and digital transition, by working together so that we can master the technologies and we can deploy them. And we can also make sure that we have the autonomy to be able to do this. That means that we have the means, the raw materials and the structures to be able to do this, so that we, at the end of the day, can have a more climate neutral, circular, and clean industry. Because that's the part of the competitiveness which is absolutely necessity for us to succeed in this area. And that means not only that we have the industry with us, but we also need all the people that are working in the factories, and we need the society to help us also launch this. Because we can come up with the best technology in the world, but if people don't want it in their backyard, then we have nowhere to go. And we saw that with other technologies which may or may not be important for the future, like nuclear energy. Nobody wants a nuclear power plant in their backyard. And we need to make sure that everyone shares the burden for this. So this cluster 4 is basically an integrating activity, and it consists of 6 destinations, which we're going to see on this slide here. And here you can see the destinations which have been discussed for the work program for 21 and 22. They may change over time, but we would like to keep them as steady as possible. And here you have the climate neutral, circular, and digital production, also called the twin transition. You have a digitized, resource efficient, and resilient industry, which we call resilience. Then you have an activity around world-leading data and computing technologies is data. And also the emerging technologies, not only in digital, but also in other areas. And then we have an area for space. And then finally, we have an area where we are talking about human-centered and ethical developments of all these technologies, which is absolutely needed if we want to be able to have also, what do you call it, a stranglehold in the society. Just to take a little bit more detailed look at the 2 first destinations, which are the most important ones for industrial transformation. Here we have several sort of separators underneath the 2 destinations, as you can see here in the slide. I don't want to go too much into this, but it's important that we can sort of cluster the activities that we have, because otherwise it becomes so complicated that we cannot really take the trends from these technological areas and then feed them back to the policy, so that we have a synchronization between the policy development and the technological capabilities that we have. And therefore, we need to make sure that we can cluster the activities in the right way, just like what you're doing here in terms of non-battery energy storage in general. So what is all this? I mean, you need, and I think that you're the experts actually in this field. I think that we all know that we need to integrate the technologies to achieve the goals that we have set. And it's not straightforward because it contains so many different elements. It goes all the way from making new composite materials for the blades of the wind powers. We need to make new coatings on different things. These are very, very complicated things if we want to make them sustainable. And that we need catalyst is pretty obvious, at least for us. But we also need other things like membranes, surface coatings, and then the whole integration of all these things along the value chain. It's really, really important, because if we cannot demonstrate throughout the value chains that we're able to do this, then we've actually reached nothing. Then we have a technology that may be very nice, but we cannot show that it actually is ready to go on the market. And that's what we have to do. So therefore, the way that we need to go about this, and I'm not saying that this has to be the same for every field that we're dealing with, but we need to design the new materials that we have according to what the system's needs are. That means we need to start with some of the materials that we have. We need to model them to make new materials, to make them better performant and more cost effective, so that we can boost the whole transition, and also make sure that the materials that we're using for all these things are actually available. Because we may have the nicest of product, but if it cannot be recycled, or if we do not have the raw materials, the critical raw materials in this case, to be able to do this, again, then we are nowhere. So we need to work along the value chain. We need to design them. We need to optimize the material. We need to be able to produce them, and we need to put them on the market. And one of the elements to be able to do this is actually pretty fundamental. I think we all, at one point in time, we are exposed to this. If we cannot characterize it, if we cannot see the materials and measure its properties, then we cannot really use it for anything. Because in order to be able to model materials, we need to have accurate data. And accurate data comes with better characterization. So for us, the linking of characterization with modeling and development of models is absolutely essential. And like this, we can make new models that will allow us to be able to make better and more efficient materials. And so that we can model the whole value chain, not just from the start, the material itself, but also to see what is the actual footprint of CO2 carbon footprint of these processes. Because otherwise we're just spinning our wheels. It should not be gate to gate, but it should be cradle to grave or cradle to cradle evaluation of the footprint of these things. And just to give you a few examples of what we're going to do in the future, and it's really not exhaustive, because otherwise I could use a whole presentation about this. But there are some essential elements of this, and we're going to pursue all the things throughout this work program, but we cannot do everything at the same time. And that's why we tried to prioritize those things that are the most important first. And one of these things is the valorization of CO and CO2 streams into value-added products of market interest. We have new electrochemical conversion routes, and I think that you're going to see several examples of some of these systems in the next presentations. But it's really, really important that we have a broad palette of different kinds of technology options for being able to do this, because the catalytic systems that we are going to need for the future are going to be completely different, or potentially completely different from the ones we have now, because we're changing the systems. And that means we also need to have an integration of hydrogen, for instance, as one of the major elements in this whole chain for replacing fossil fuels. And this is not going to be easy. It's going to take a long time before we're able to do this, because I think we all know that making hydrogen has a big energy penalty. And the more we can reduce this energy penalty for making the hydrogen, the more we can have hydrogen available to use. And that, of course, takes, as I already said, different kinds of catalytic conversion, and also changes of the catalytic system that are already available. Because at the moment, we're using fossil fuels to heat many of these systems, and we need to change that so that we can use electricity instead. And at the same time, we need to have a community around this, because if we do not sit around the table and try to form this together so that we make informed choices about the future, we are not able to do this. The political system is simply not geared for this. And we need people like you to come and advise us. And that's why we need to form a community for solar fuels and chemicals also for the future. And it's one of the first calls. We will have a deadline here on the 23rd of September. So I'm looking very much forward to that. And my final concluding remarks is simply that we must integrate all these technologies into the value chains, because otherwise we are facing bottlenecks inside the system. And therefore we need to be sure that we can open those. And we can only open those if we are able to demonstrate at the end of these value chains that we can make the materials. That does not mean only to look at very high level TRLs. It means to look at the whole scientific value chain as well, to make sure that we have new technologies all the way from TRL 2, 3, and up to actually industrial production, so that we can test this, and we can only do this together. So with that, I would like to thank you for your attention, and you can get some more information also about HADEA, which is a new, what do you call it, agency on the blog. And I'm at the moment, I'm heading the industrial technologies of that. So I'd like to thank you very much for your attention, and I wish you all the best for the rest of the workshop. Thank you.
Thank you so much, Søren, for such an inspiring presentation. It's been a pleasure to have you as to do this opening short talk. So thank you so much. Next is Christian Kalusev. The floor is yours, Christian.
Yes, thank you, Pablo. I will just share my screen. Can you all see my screen?
Yes, we can.
Good, thank you. Yes, I am here to talk about the RECYCALYSE project. It's a part of the topic from the previous Horizon 2020, which we are talking about today, the materials for non-battery-based energy storage. The project is about new sustainable and recyclable catalytic materials for proton exchange membrane electrolyzers. And the partners for the project are, first of all, I'm from DTI, the Danish Technology Institute. Then we have TWI from UK. We have the Technical University of Freiberg from Germany. Sustainable Innovations, where Pablo is from Spain. Profrex from Germany. Agorec from Germany. University of Bern from Switzerland. Blue World from Denmark. Center from Austria, and Fraunhofer ICT from Germany. So we have a mixture of both academia and industry. And the next slide is very much in line with what Søren just talked about. So this project fits within the agenda of non-battery-based energy storage. It's about power to hydrogen. And so storage of sustainable energy, as Søren also talked about, is predicted to play an essential role in the future of a low-carbon energy system. And energy storage from renewable sources in hydrogen is very attractive due to the high energy density, the stability and the potential low cost of the conversion, as well as the improved coupling to other sectors with many different applications like electricity supply, industry, mobility, e-fuels, and so on. Hydrogen can be produced from electrolysis, and that could be from renewable energy sources, and it can work as an energy storage medium. It can also help to overcome the irregularities of renewable energy sources. And then it can possess a very great potential to limit the use of fossil fuels in the near future. So on to electrolysis. There are several types of electrolyzers. I've listed some of the most well-known, which are first in the development. We have proton exchange membrane electrolysis, we have alkaline, we have solid oxide. They all have different pros and cons. This project is about proton exchange membrane electrolysis, or PEM electrolysis, where water is decomposed into oxygen and hydrogen using electricity. The PEM consists of an anode electrode, typically with an iridium-based catalyst. We have a cathode electrode with a platinum-based catalyst. And then we have a proton exchange membrane separating the two electrodes. This whole construction we call the membrane electrode assembly. And this membrane, it allows for protons to travel through to recombine and produce hydrogen at the cathode. The use of this membrane, which has a low ohmic resistance, has several advantages. First of all, it enables a very high efficiency of the PEM. It can operate at very high current densities. It can produce hydrogen at high pressures and also with high purities. And then we need no safety equipment for operating the system. We use only clean water. This project here is about the materials at the anode, which are the most expensive and where materials development can have the most influence on the performance. And I will a little bit deeper into that. So the anode materials typically consist of these critical raw materials, iridium and also sometimes ruthenium. They are also called platinum group metals, and they belong to a group of extremely low volume elements. So they are first of all very expensive, and they are not produced in very high rates. It's only around 10 tons a year for both of them, which is very low. And they have very huge CO2 emissions during the mining, especially for iridium, and they are also mined outside EU. And all this causes significant barriers for the economy of these PEM electrolyzers and for hydrogen storage production. Actually, iridium and ruthenium are byproducts of platinum mining, so we have platinum also at the cathode, but used in smaller amounts. All this tells us that we need new improved materials for us to develop the PEM electrolyzers. So we need increased performance, reduced total cost, and increased recyclability. And this is in fact what the project is about. So we have here in the electrolyzer part, we address the entire value chain of the PEM electrolyzer, all the way from the catalyst manufacturing to the system integration and the demonstration to end-of-life recycling, and then to supply raw materials for the catalyst manufacturing again from the recycled materials. The goal is to overcome the main existing barriers for PEM electrolyzers to penetrate the market, namely the price, accessibility, and performance of electrocatalytic materials. And to achieve this, we have two main objectives. First of all, we want to develop and manufacture highly active, sustainable oxygen evolution catalysts, which will reduce and eliminate the use of critical raw materials, thus decreasing the CO2 emissions and reduce the cost. And then we also want to establish a recycling scheme for the proton exchange membrane electrolyzers catalyst, for the electrodes, and for the overall system. And by implementing all the recovered elements here in the new developed catalyst from Objective 1, we will decrease or reduce the dependence on materials import in Europe, and we will reach a circular economy. So the circular economy is also depicted in the concept of the project, where we go with, you can say we start with the catalyst production, where we need raw materials. We integrate the catalyst materials in electrodes for the device fabrication. These electrodes via what we call membrane electrode assemblies are utilized in electrolyzers for the production of hydrogen. Then we look at the spent membrane electrode assemblies, see how can we recycle the materials, both in terms of recycling the critical raw materials themselves, creating new metal salts, new precursors for the catalyst production, but also looking at these membrane electrode assemblies, how can we reactivate them, utilize them again for new device application, and also how can we recycle the entire system, looking at, for example, also the titanium flow plates that are used here. All this is also reflected in the expected results. We have a result where we expect to have new stable catalyst materials with improved activity. We have more or less three groups of materials. We have supported iridium ruthenium oxide catalyst. We have a catalyst with reduced critical raw materials where we alloy these catalysts with earth abundant elements, but also look at completely critical raw material free catalysts. We look into how to efficient manufacture these catalysts. We look into how we can scale the recycling processes for critical raw materials and other elements contained in the catalyst, such as nickel, manganese, and copper. We look at recycling of the spent MEA, is membrane electrode assemblies, utilizing reactivation. We look at the strategies for the overall PEMIC system, and then in the end, we want to have a circular economy by reusing the recycled materials to prepare fresh catalysts and reactivated membrane electrode assemblies. Related to the concept, our project consists of 5 topics. We have materials, where we look at both catalytic sites and support materials. We have fabrication, where we look at fabrication method for the catalyst, and we look at fabrication of electrodes and MEAs. We demonstrate the electrolyzer systems where we use MEAs from the fabrication in a stack. And then we look at circular economy, where we look at the materials recycling. And then we also have a outreach and business development for the results obtained in the project. So now I will give a small run through of the different topics here, and then I'll give some highlights of the results achieved so far. The project is almost halfway through. It's a 3-year project, so a lot of these things will be preliminary. Our approach, as I briefly mentioned before, for these novel electrocatalysts is to utilize support structures. This is inspired by fuel cell catalyst, where you use carbon supports, for example, for platinum nanoparticles. But here we have much higher demands to the support because of the high potentials and oxygen atmosphere here at the anode. So the use of a support will enable the use of smaller catalytic particles. This will give a higher surface area and thus higher activities, but at the same time the support will make sure that we still get nice porosities in our electrodes. The use of the support is then combined with the development of new catalytic sites by alloying iridium and ruthenium, for example, with non-critical raw materials such as nickel, manganese, or copper, and also by synthesizing new completely critical raw material free catalyst. We also want a protocol to determine the activity across the entire consortium, so we are sure that we are all following the right path and we can compare our results. So for the fabrication, we are looking at combining the catalyst sites with the support and looking in how to upscale the fabrication of these. Sorry. So some of the objectives here are to optimize the production of these combined structures. We want activities higher than state of the art, and we want a high stability of the materials. And we also look at how to produce at least 50 grams an hour of the materials. And then we need to prove that we can actually reuse some of the materials we will recover later on in the materials recycling topic of the project. We also look at the electrodes and the single cells, how to incorporate these materials, how to optimize the catalyst ink for the deposition onto electrodes. We want an optimum utilization of the catalytic activity. This ink is going to be a bit different from, for example, from standard iridium black catalyst because of these support structures. And we want to optimize the manufacturing of electrodes and MEAs in terms of scalability and performance. For the demonstration, we will assemble a full PEM electrolyzer system using the materials from before in a developed stack. We will develop an electrochemical model combined with an overall system model for an optimized PEMIC system. Then we will test the functionality of the stack and the system. And for the first version of the stack, we have defined the specifications. We have assembled the stack, which consists of 14 membrane electrode assemblies. We have prepared the test stand for the stack. We have developed a control strategy for the test stand. And this control strategy is simulated based on information from the materials development and fabrication. And it contains both a control model and a stack model, and we should be ready for a demonstrator test next month. So moving on to the circular economy, where we look at the following objectives for materials recycling. We look at the recycling processes for the recovery of the critical raw materials. So it's recovery of these platinum group metals, iridium, ruthenium from spent catalysts, where we want to achieve more than near 90% efficiency. And then we also look at the separation of the elements for iridium, ruthenium, and platinum from additional metals in the catalyst or from contaminating elements. We also look at reactivation of electrodes using cathodic reactivation, where we can directly reuse the membrane electrode assembly. And then we also look at the recycling of the whole PEMIC system, where we want to create a scheme where we also get the titanium flow plates. So we've developed a scheme where we first do an automated dismantling of the titanium flow plates and the MEA structure. The MEA is then pre-treated in an alcohol water mixture to dissolve the catalyst materials. We call this the dry residue. And we want to dissolve that from the membrane and the electrodes. And this residue is then leached using a hydrochloric-based solution, creating PGM chloro complexes. Here we have achieved leaching efficiency, in this case for platinum up to 100% and for ruthenium up to 90%. And we then refine these complexes, creating the final PGM precursors, which is then followed by a separation step, volatilization for ruthenium and precipitation from platinum, where we can get the individual precursors. These precursors are now ready for us to test them for synthesis of our materials. So, as mentioned before, we are halfway through the project. And if we keep the goal in mind that we want to overcome the main existing barriers, which is the use of these PGMs, we can see that the usage of these support structures has a great potential for reducing the critical raw materials. We're already now actually beyond state of the art by using support before we have making the alloying of non-critical raw materials really work. This is still work in progress. We can see so far that the use of completely non-critical raw material catalyst can be a very huge challenge. It's still also work in project progress. We need still to optimize the material utilization in the membrane electrode assemblies. We can see so far that we can most likely lower the catalyst loading quite a lot, also with the current materials, while keeping a good performance of the membrane electrode assembly. The first generation stack, as I mentioned, is ready for system implementation and demonstration. We will have a second generation stack to produce later on the project, and recycling on the project developed materials is in progress, and we are now ready to use the first precursors for new catalyst. With that, I would like to say thank you for your attention.
Thank you so much, Christian. I would like to give the opportunity to our attendees if they want to ask any question. For example, we had one before. Let me read it, Christian. You can also participate, the rest of the coordinators. I've came across some alternative energy storage, which is saltwater potential to keep a charge. As I'm pretty convinced it's the alternative I would like to improve and adopt. May I know if can you provide with your opinion on exploring this source, if not suggestion of what is the best alternative?
I must admit I don't have an answer to that. I'll just see if I can see the text myself.
Yeah, it's the first one.
Yeah, I'm sorry, I do not have a question for that, answer for that.
Okay, specifically, I think because I think this question was coming during the Soren speech, so I think maybe in the upcoming presentation we are able to answer that question. There is one specifically during your presentation, Christian. What is the cost of the recycle process of the proton exchange membrane?
Yeah, that's a good question. This is, we are not in an upscaled process yet that we can actually answer that. But the whole idea is, of course, that the cost should be lower than the mining, and also that the CO2 production will be lower.
Okay, and I think that's, yes, we have, how stable are the ERU-CAT? Did you perform some tests?
Yeah, we have some preliminary results that I cannot show yet, but it looks very promising. Also, actually, also in the single cell test. So it's about when are you ready to show the results, but it looks promising.
Okay, an additional question. Is it realistic to have proton exchange membrane electrolysis completely without critical raw materials elements?
Yeah, I mean, we are trying that in our project, but we also see that it's a big challenge. And I would see currently, I would say the most likely outcome is that we'll have a strong critical raw material reduction, but we will not get rid of it.
Okay, more questions seems to be coming up. Do you have in mind to make several cycles of recycling to see the real recyclability? How many?
No, in the project we'll only have one cycle, but it might be something we should consider.
Okay, and the last question we have is, hello, what is the bottleneck of the recycling process?
I'm actually sorry that I will not be able to answer this question. It will be the Theo Freiberg who's in charge of this. I will not be, I cannot be, I'm not the expert on that part of the project.
Okay, I think most of the questions can be also answered with the rest of the presentation. So we invite you to keep the workshop. You may find the answer in the upcoming presentation.
I know that the other members of the consortium are also here, so they might also be present at this breakout session.
Okay, we don't have more questions regarding Christian's presentation. I think we should move to the next one. Who is Jose Luis Viviente, project coordinator of AreNHa project. Jose Luis, the floor is yours. Just give me a second. Now.
Yes, yes. Do you see my screen? No, yes, no?
Yes, we can.
Yes. Okay, thank you first to invite us to participate in this workshop, Pablo, or RECYCALYSE Project, let's say. My talk will be about the AreNHa project, that is advanced materials and reactors for energy storage through ammonia. So as you see by the title, it's regarding ammonia as a hydrogen energy carrier. Sorry. It doesn't move now. I used to try before, it was working.
No, do you want to try again? I mean,
Yes, it's no. Let's wait a moment. I'm going to escape from the.
Now, try to share one more time. If not, remember I have your presentation. We can.
Yes, no, but I've been trying this. Okay, I know what is happening. Compartir. I have to do. Sorry. Wait a moment. I want to do something else. I'm going to escape. Yeah.
If you want to do a final test.
No, I will. No, I should work. Don't worry, it should work. I will do the last try. Don't going to hide the review, the presenter view. That's the point. So now I'm going to share. This will be the last one. It's okay now.
We see your presentations. Try to move.
Okay. Yeah, I'm going to. Sorry.
Don't worry, Jose Luis. If you want, I saw the presentation and you let me know.
Yeah, I think it's better. I know I was trying before. I don't know why it's happening now. Because we tried it.
It may depend on where your cursor is. Sometimes if the cursor is in another window, it doesn't respond.
Yeah, but I just tried the same layout now.
Okay.
as before. So that's why. Okay.
Can you see the screen now?
Yes. Yes, I can see the screen.
Okay.
And so let's go ahead. I will go. Yeah. Okay. This has been also stated by Soren before, that renewables energy is nowadays playing an important role for addressing the low carbon economy and addressing challenges that we are facing regarding the climate change or the energy security, non-depending of external countries in Europe, or also regarding cost of energy. So the point is to have this renewables energy storage is crucial, because the renewable energy are intermittent. So we have to address this no matching demand and offer between the renewable energy we have, and between the options we have this that from a sustainable way is to have the solar or wind or tidal as well energy, that we should have the capacity for to integrate to be connected to the grid. So we have to address this intermittency, and the only way is to have good storage capacities. There are several solutions, but I will show you later on some figure where we see how long we can store and what is the amount we can store. So what is the best technology? So batteries must not be the best solution to fight these energy storage needs due to the cost, safety, and environmental issues. And also pumped hydro methods or compressed gas energy storage, they could suffer from geological constraints for the deployments. Next, please. Next. Okay, so in this graph, you can see was also written by Soren in the first talk about what is the different storage technologies, but which could be the one that could have a largest storage capacity and also a large frame of release time of the storage capacity. As you see, you can have from the electrical capacitor, you have superconducting cores, you have flywheels from the mechanical technology, you have the battery, several batteries, and then you move to the mechanical, let's say compressed air or pumped hydro, and then you have the chemical, methane, ammonia, hydrogen. So that has a longer time and also longer capacity. And that means they could also have, but you see, it could be from 1 hour to 1 year is a figure from this reference. So that means the interest to have a chemical storage capacity methods. Next slide, please. So the non-battery based storage technologies has powers to X, like power to gas, power to chemicals, or power to liquids, that could transfer the renewable electricity into synthetic gases, hydrogen, methane, or other gases, or chemicals, are the more suitable solution for different energy storage needs. So the point, we have to have sufficiently flexible mechanisms to allow large quantities of energy to be stored over long time periods at any location is chemical energy storage via hydrogen or carbon neutral derivatives. Just click one more time, please. So between this, hydrogen has gained considerable attention as an ideal and clean energy carrier, because they produce water as byproduct and has high efficiencies for energy conversion when it is employed as feedstock for power production. But one drawback is the low volumetric energy density and difficulties associated with gas handling of the hydrogen. So the best way, just click one more time, the solution is to have the hydrogen stored as in chemical bonds or hydrogen carriers compounds. So this next, use press. Yeah. Why ammonia? Ammonia because has a high volumetric energy density between the non-zero carbon fuels. It's higher than the one we can obtain if in hydrogen. It has a relative low cost, easy to be liquefied. It can be liquefied at room temperature with 7.6 bar G, for instance, or 36 or 33 centigrade degrees degrees 1 atmosphere. Easy to store and transport. We have already large knowledge about the transport and storage of ammonia due to the use of ammonia for fertilizer as a feedstock for developing fertilizers and their chemicals. And the main issue is carbon free. We have ammonia is nitrogen and hydrogen. Just click one more time, please. So we can store it the time we need, and then we can use directly for energy production or as fuel for internal combustion engines or fertilizer. And also you can also produce hydrogen via ammonia decomposition for using hydrogen in fuel cells for electricity power production or for a hydrogen refueling station. So for mobility. So here you can see the different fuel range of fuels and the volumetric energy density. As you see, the zero carbon for the zero carbon fuels, the higher volume energy density is the ammonia, as I told you before. Use next slide. This is why this why the AreNHa project aims of using ammonia as a green hydrogen carrier. And for that purpose, it develops his main activities around the green hydrogen production, ammonia synthesis, ammonia storage, ammonia decomposition, other direct energy use of ammonia. It's a 4 years project with funding of around 5.7 million euros. Use click again. So the main goal is to develop, integrate, and demonstrate the key materials solution, enable the flexible, secure, and profitable storage and utilization of energy under the form of green ammonia. And in the project, click again, please. In the project, we are going to demonstrate, the full power to ammonia outside value chains at TRL5, and the potential of the green ammonia to address issues of large-scale energy storage. Just click twice because I think just go through this because I will explain with the overall figure. I think it's better. It's not going to repeat things. Just click several times to the figure. Yeah, because I will talk about this. You will have in the presentation, but let's go to the next one. Click once more, and once only for the first slide. Yeah, okay. The partnership is, we have 11 partners from 7 countries, in which we have 5 SMEs and industries and 6 research centers and universities from around Europe. Let's move to the next slide, please. Here you see what we're going to do in the project. We are going to develop new materials and processes at lab scale for the green hydrogen production with high temperature electrolysis. That was solid oxide electrolysis cells. And also we are going to develop nitrogen through electrochemical process, as well ammonia through electrosynthesis process. So green, also nitrogen and ammonia production. Then we are going to develop ammonia through advanced Haber-Bosch process. And then we are going to develop solid absorbents for solid storage. And this we will use for, we are going to work in the for hydrogen decomposition for membrane reactors to produce hydrogen that will feed PEM fuel cells and also refueling station, hydrogen refueling station. And we will also study the direct use of ammonia for production of power through solid oxide fuel cells, and the use of ammonia in internal combustion engine. So in the activities related to the ammonia synthesis will be the hydrogen synthesis with SOEC will be developed by Fraunhofer and Elcogen with their own SOEC layout. They are high temperature, but one I think working at 650 degrees for Elcogen. They are anode. Yes, I have the names here. They are anode supported cells for Elcogen and electrolyte supported cell from Fraunhofer. But I think the one from Fraunhofer is working at higher temperature, around 750 degrees. And DTU, that is the Denmark Technology University, is working in developing nitrogen for electrochemical production and ammonia for electrosynthesis, and also for developing absorbent for the solid storage of ammonia and absorbent to be used in the Haber-Bosch process for ammonia synthesis. And the catalyst for ammonia synthesis will be developed by the English partner, that is the United Kingdom center. And they will also develop absorbent for the Haber-Bosch process, D2, and catalyst for the Haber-Bosch process, and also for the low temperature catalyst for the decomposition of ammonia. And then Fraunhofer will work on the use or direct use of ammonia from solid oxide fuel cells. And Peugeot, that now is Stellantis, will work in the ammonia used in combustion engines. Just click once more time. So the idea in the project is to we do new materials and process a lab scale, but then we develop prototypes that will different types that will be integrated in the facility of Centro Nacional of Hidrogeno. They have a facility where they have a photovoltaic plant that can feed the electricity to the prototype that will be developed by Elcogen or IKTS. Both will be tested, but for the final integration, one will be selected. The idea is to develop a small prototype for producing 1.5 normal cubic meters per hour of hydrogen. That could be a SOEC system of 5 kilowatts electricity. And then the Haber-Bosch, the idea is to develop a new system to be able to work at lower pressures. And nowadays, the standard pressure is between 150 to 300 bars. And the idea is to reduce to the half and below 50 bars. And also to work at low temperatures, lower than 450 degrees, but using the new low temperature catalyst developed by the English partner. And on the other side, we will have also a tank for the prototype, and the decomposition prototype will be able to produce 10 normal cubic meters of hydrogen per hour. So they should integrate maybe 55 membranes or something like this, more or less. And this each one will be tested at the facilities of the pilot plant of the Centro Nacional of Hidrogeno in Spain, where they have the fuel cell, where they have a refueling station. They also have hydrogen production if it's needed for the prototype, and also nitrogen production unit. So they will be tested standalone and then all of them integrated together. Let's move to the next slide, please. So the idea, we have the development of the materials. We have for all the system, we have the modeling part, and also for all the system we are studying, I described before, we have a modeling section, also for all the system, integration of the system as well. And then we have work package 4 is to develop the components for the prototypes, for the demonstration. And then we have the validation of Centro Nacional de Hidrógeno. Proton Venture is the company who is developing the Haber-Bosch process. I forgot to mention. And then in parallel, we have the business case that will be led by ENGIE, a French company, and addressing the market value chain and go-to-market strategy, IPR. So the go-to-market and business implementation of all these technologies. And also we will have an work package dealing with societal acceptance, economical life cycle analysis, and also life cycle cost analysis, and safety assessment, where ENGIE is leading, where also Centro Nacional de Hidrógeno is we are all involved, but main actors are ENGIE and Centro Nacional de Hidrógeno. And besides the dissemination and communication activity and the management activity. Just move to the next slide. So main impact is we have several impacts from the project. We decrease the energy import dependency because we could have the possibility of using ammonia as fuel. We promote the integration of renewables offshore or onshore renewables for energy dependency. And also because we deal with the peaks when the demand is, we have a higher offer of the renewables that is not should be stored or is not used because it's not used in the grid. So we can develop hydrogen and have the ammonia for this. So we facilitate the integration of renewables in the power system with large scale energy storage, and also I would say the whole range of energy storage somehow. So we also promote the strategic European leadership in energy storage and developing new technologies. And also we open the possibility to develop ammonia, to use ammonia and as a fuel supply, energy supply from other countries besides the European countries, because we can develop also in Europe. So we are developing alternative energy import or fuels that using the renewable electricity storage and long distance transportation. I think it was a document from the Royal Chemical Society in England, where there's a figure where we can see that the cost of transport of ammonia is very small compared to hydrogen transport from the in train or in road transport and in ship transport as well. So that's why ammonia is an interesting zero carbon fuel. So this could be increase the revenues for 2.5 trillion per year, to increase the number of future works jobs in Europe, and also a very important issue is to reduce the NOx emission in the process we are dealing with. And also we avoid the use of we could avoid to use 20 million barrels of oil per day. But let's move to the next slide, please. So as a summary of activities, we have already set up our website. As I told you, it's a 4 years project. We are in the more 15 of the project. We have around 3 publications, one of them in a long paper in a proceedings of a conference. We, including this and the next conference next week, we have participated in 5 workshops. We have already do one patent request regarding the decomposition integration with clean system. And also we have released 2 newsletters, and then other press, we have a video, some reports that could be seen in the website, and you have a LinkedIn. Also, you can access and you can ask to adhere to the LinkedIn or Twitter in the website. Just click the next slides. Now I'm going to present some status on the progress. And regarding the business case definition, we have already identified initial market. We have done some initial market analysis to identify promising opportunities for ammonia as energy storage solution, and also to identify key stakeholders and competitors in the field. We have done an initial value analysis of the value proposition of the AreNHa concept, also identifying the state of the art of the technologies, and also to underlining the peculiarity about the developed concept, and it could be the impact of the concept in the end user, assessing the state of the development at the end user project. Because this will be case by case, and depending on the situation, then the cost is a main impact as well for the business case. Just click again, please. Yeah. So regarding the modeling, and the work package on design and modeling on the system and the complete value chain, we have already defined the industrial requirements and the battery limits between the different components and prototypes we are developing, because at the end we need to integrate them. It's true that we can have from the storage, you can have all the previous system connected, and later on you can have the storage connected to the composition unit and to the hydrogen production from the composition of ammonia, or the storage to the use, so that this can be splitted. So we have done some preliminary process flow diagrams of the SOEC system as well as the hoverboard demo unit, and we are applying modeling tools to identify optimal materials using computational searches. And the idea is to compare this with the experimental tests we will do with these materials, but this allows to select select previous identify suitable candidates for the materials. And we are also optimize this for the ammonia absorber. And also we have done some kinetic studies of the selectivity of the ammonia reduction versus hydrogen evolution in ammonia electrosynthesis. And also regarding the ammonia decomposition operating condition, I will show you more details on this, because as we have a patent and we have protected this, we can disclose some more information. And also some experimental kinetic data on membrane reactors model and definition of the best suitable working condition. Okay, please check. So regarding the components development, well, of course, we have an impact due to the COVID, and also for the work pace and so that's we have tried to avoid delays in the prototype development, and for the lab scale we can have some margin because they are not going to impact in other work packages. So we have already developed SOEC for the first test on using thinner electrolytes and improved electrodes for the EKTS layout. And also we have Elcogen has already also developed some different air electrolyzers to improve their already SOEC system. We have also developed some absorbent materials for Haber-Bosch process. And they have been identified by modeling, and we have already synthesized and done some, we start some characterization. So that's along the last months. We have done some electrochemical synthesis of ammonia materials for support and electrolyte selected by DTU. Tecnalia has already prepared several palladium-based membranes for hydrogen separation, and also we have been working on palladium recycling for the palladium membranes. And the Eindhoven University of Technology has already done some lab-scale permeations tests using single gas or mixture of hydrogen, ammonia, hydrogen, nitrogen on the palladium membranes. And also they have done some tests, decomposition tests using palladium-based membrane reactor using ruthenium-based catalyst. And we can achieve more than 86% of hydrogen recovery with a purity of 99.99.8% as one of the main results. And we have already developed by the English partners some ammonia synthesis catalysts based on light metal amides that should work at lower temperature. And Peugeot, with a third party, University of Orleans, has already done some tests for using pure ammonia in combustion engines, and studying also the engine working condition, as well as increasing the amount of hydrogen up to 10%. Just click the next slide, please. So I go to show some results from the membrane reactors. The idea to use membrane reactors is because you have the decomposition of ammonia into hydrogen and nitrogen, and you have the separation in the same place. So you have less systems. You increase the efficiency of the process, so you can decrease the size regarding to standard non-membrane reactor for ammonia cracking. So you can achieve the higher separation, hydrogen and efficiencies and conversion at lower temperatures and with higher values. And as using a single unit, you also reduce the footprint of this technology. So I'm going to show you some few results. Please click next slide, please. So here you can see for the packet bed reactor, the blue colors are for packet bed reactor without membranes. Then you have the green is the packet bed membrane reactor, but with the permeate at 1 atmosphere, 1 bar, and the red color you have the permeate with vacuum. You have here the experimental conditions. So and the delta P3. So as you see, with the packet bed membrane reactor, the conversion is limited and cannot be reached cannot reach the thermodynamic equilibrium conversion. That is this line here. But when you use a membrane reactor, you increase the conversion, and when you are around 425 centigrade degrees, the conversion is already nearly 100%, and is higher than and is near over 90, yes, near 100%, and is over the thermodynamic equilibrium. And if you do the vacuum, you go nearly to the 100%. And here on the right, you see the purity is over 90% with the membrane vacuum. And recovery, the recovery is over 90% in all the cases for the three temperatures, 440, 425, and 450 degrees. And you see how the driving force for the permeation affects the hydrogen recovery. If you click to the next slide, you see the effect of increasing the pressure. We have studied the effect of the pressure, the effect of the temperature, the effect of the ammonia feed flow rate, and also the effect of the permeate pressure. And here you see is when you at 450 degrees, you have nearly nearly 100 ammonia conversion for all the pressures. You have a higher hydrogen recovery when you increase the pressure, but the purity is decreasing until 99.98 when you go to 5. 2 bars, we are around 99.94. That is one example. So go next slide, please. Yes, one question would be, what was the long-term behavior of these membranes? As you could see, this is 300 hours test, and the ammonia conversion is constant, and the ammonia recovery keeps in a bit because maybe there's some cleaning process in the surface of the palladium membranes, but you have more or less a constant hydrogen recovery, and you see the purity of hydrogen is also constant, and the ammonia in the permeate is around 50, okay, maybe 17, between 50 and 20 ppms. Go to the next slide. So you have noticed we have some ppms in the permeate side of the membranes. So as far as I know, the highest amount that the fuel cells stand is 0.1 ppm to avoid any contamination in a PEM fuel cell. And then we have done some tests, preliminary tests, using a zeolite, commercial zeolite 13X as a solvent material, and we have noticed that with the solvent materials we are able to capture the ppms, and we have to work because due to the resolution we have to check how down we go. Is we are under 0.1 ppms, but this will be in the future. Could you go? I think this is the last slide. Thank you. If you have any questions, yeah. I'm going to see the chat.
Yes, thank you so much, Jose Luis. Yes, we have now the Q&A section. So we have some questions, so I'm gonna read it. Some of them have been already answered in the chat, but I'm just gonna read it again just to make sure that everybody read the question. So one of the questions is, why producing N2 electrochemically while you can just take it from the air?
Okay, yes, a good question. I know the expert in the field, and that's I could say I'm more in expert in the membrane area, and I think that we are trying to develop. That's why we stay a low lab scale. We have to check what is the efficiency of the process. Here, the idea would be to use electricity to do this. Not so I guess to go to implement this further develop to higher TRL, they should check the efficiency and the cost of this process. But it's true that you have already nitrogen in the. I fully agree with Philippe in this case on this.
Okay, the next question we have is, how could we reduce the NOx when using ammonia at?
Ammonia at.
Then we have the same question, how could we reduce the NOx when using ammonia as full?
Yeah, okay. I'm not involved in the field, but I guess they need to recirculate, or they should have. For instance, I have this paper from the people from the internal combustion engines, and there are the companies, car, Peugeot, that the ppms, and it's no of ammonia, NO2, NO or NOx, let's put it in this way, they are in the thousands of ppms in the range. They're very high. They have to deal with this if they want to promote the use of fuel as a as you want to promote ammonia as a fuel, because you cannot release you don't release CO2, but you release other dangerous things. But I think they're thinking on recycling or having some absorbent or something. I don't know how, because I don't know I don't have expertise on this.
Okay, one more.
But they have to they have to decrease this to zero, this, because it's not you go to something bad is having CO2 emission to something worse, maybe NOx. It's not so good as well.
Okay, we just get a few more questions. How do you explain that an increase in pressure does not affect the NH3 conversion?
How do you
then the last one?
The last one.
Before
okay.
the last one?
Yes. Before what is the best way to transport ammonia?
It says, nice presentation. How do you explain that an increase in pressure does not affect the NH3 conversion?
How could you explain why? Could you please repeat the question, because I cannot find in the chat, in my chat, the question. How do you explain?
How do you explain that an increase in pressure does not affect the NH3 conversion?
You see in the figure we have. Okay. The point is the range of pressure we are working with, and I think we already are in mainly the 100% conversion. As I look to the graph, there is a minor. I think we are nearly over 100. I don't know if you can go to the figure, because it's on the slides in the presentation back. Because as you see, I think the numbers are really near 100 or 100. You just go to the back in the slide. You can open the slide with this. Is the slide number 19?
So let me know
when previous one. This one. No, previous one. This one. Okay. You say the question is why we don't see an increase in ammonia conversion due to the increase in pressure. No, this was the question, no?
Yes.
Yeah, but I think the range we are talking about here is of pressure is small, and here I think we are nearly at the same value, but we are already in 100%. I don't have the exact values of this one, but we are already, because at 450 degrees we have already 100% full conversion. So I don't think we can have a higher increase. We are talking about ppms, I guess. I don't have the absolute values of this. I don't have, but you see on the left is 100 already.
Okay, we are gonna. I see there is more questions. As you know, you have the here in the slide the email of Jose Luis Viviente in case you want to go deeper any topic. But for now, I would like to give you 10 minutes break. I hope you enjoyed your 10 minutes break. I would like to give the word to Jensen, who is the project coordinator of NextArc. He will explain us a little bit about the project, methodology, scope. So Jensen, the floor is yours. Let me stop sharing my screen so you can.
Thank you very much, Pablo. And first of all, thank you to you and the RECYCALYSE people for taking the initiative and arranging this workshop for all of us. I think that's a good thing. And I will just share. It should be here.
Yes.
You see? Very well. Well, first of all, the title of the course, non-battery, is something that is nice sometimes. Us hydrogen people are under some pressure from the battery sector. The battery vehicles are pushing against the hydrogen vehicles. So that's a kind of creative competition. So sometimes it's nice to focus on the non-battery concepts. That I do appreciate. Well, next AEC is about alkaline electrolyzers. We are developing new materials to make what we call the next generation of alkaline electrolyzers. It started in April last year and it's going to last for 4 years. And the partners here are several universities and research institutions, but also a few industries, and that is the Blue World Technologies that we have already seen appearing as a logo. It's a fuel cell company, but they are also involved in electrolysis. And then we have Nel Hydrogen, the Norwegian, one of the leading companies in electrolysis. Basically, they have continued the tradition from Norsk Hydro with large-scale alkaline electrolyzers, but today they are also addressing PEM electrolysis. Yes, and the idea here is that we should try to develop new alkaline electrolyzers with the performance comparable to that of the PEM electrolyzer. We believe we can do that. We'll not rely on noble metals. All electrodes and all components should be made without any noble metals. We do that by means of a new membrane concept that I'll briefly explain during this talk. And it's a non-porous membrane, but we believe it can be as thin as an ion exchange membrane. So just an alternative to the ion exchange membrane that many groups are trying to develop these years. We are upscaling the components to a degree where we can do a demonstration in the Nel electrolyzer. And the motivation behind this is, of course, to improve the technology and the rate capability, but also to have a fully scalable technology that we can take to the multi-megawatt, even the terawatt level. Very briefly, we have heard about the importance of energy storage and the